My name is Mitch Weisburgh, and let me just show my screen. So, and welcome to today's webinar, which is on cognitive science and the new better way to teach math with Phil Kellman and Christine Massey. Before introducing Phil and Christine, I just wanted to make sure that you all are familiar with GoToWebinar. On your, you should all have a panel on the right side of your screen. Right now, it'll be muted because only the panelists will be talking during this webinar. But you can ask questions. So you see that there's a questions chat area on the right, and you can type in a question. And we have two cognitive scientists in the wings answering your questions. And in addition, we'll be monitoring your questions, and if we can fold them into the discussion with Phil and Christine, we'll do that as well. We'll also be recording the session, and we'll let you know as soon as as the archives are available, in case you have anybody else that you'd like to view the session also. So let me now introduce, give a brief introduction to Phil and Christine. Phil is a professor at UCLA Department of Psychology and chair of the cognitive area. He's director of the UCLA Perception Lab and founder and president of Insight Learning Technology, which is our sponsor for the webinar. Phil is also a published author. He's published books and many articles in academic journals. And Christine Massey is also a professor at the University of Pennsylvania. She's Director of Research and Education at the Institute for Research in Cognitive Science, and she's been a member of a number of different councils and committees studying learning and 21st century skills and math learning, and she's also a partner in Insight Learning Technology. I'd like to take a minute also and introduce Insight a little bit. Insight was founded in 2002 to use the latest findings from cognitive science to change the way we learn. And it's doing that in a number of different fields. It's had quite a few grants from government and major organizations, and over the past 10 years has been developing different algorithms for teaching in different fields. Their first 3 math products are actually available now. There's one for elementary students called Operations in Algebraic Thinking, with about 4 or 5 more to follow over the course of the next year. And there are 2 for middle school and high school students. Both the current ones dealing with algebra, and we'll be using these as examples of how cognitive science has affected math teaching during the course of the webinar. And if you are interested in the Insight programs, then we are looking for early adopters, and here are some of the benefits of being an early adopter. And if you email us at info@insightlt.com, or if you go to the website math.insightlt.com and you register, we'll talk to you about what's involved in becoming an early adopter. What I'd like to do first, before going into the meat of the presentation, is to just find out what areas you all are interested in. So I'm going to launch a poll, and if you can click on the areas that are most interesting to you as far as math teaching, and submit. Okay, and let's just check the result. Oops, and let me share it. And we can see that there's a good mixture, that about half of you are interested in high school, half are in elementary, a lot of you interested in middle school, and some of you interested primarily in teacher training. And so as we move on to the presentation itself, we'll make sure we talk about all of these areas. I'm going to make Phil the presenter. Okay. And Phil, are you there?
Yes, I am. Good morning,
okay.
Mitch, and some of you, it's not morning, so we're bi-coastal on this, and so maybe completely national, depending on where everyone is from. Thanks for coming today.
And Phil, can you share your screen now?
Yes, that's not what I'm. At the moment, I've clicked Show Screen. How's it doing?
Because I can't right now see your screen. Okay. There we go.
Is it working?
Yep.
Great.
And let me ask the first question actually to both you and Christine, because there's a little bit of confusion, because I keep on hearing terms neuroscience, cognitive science, cognitive psychology, learning science, learning theory. You know, we all talk about these terms when we talk about studying the brain and how we learn. You know, what do you two call yourselves and why?
Well, I think our best identification is the emerging field of cognitive science. I've put up a graphic here. Cognitive science is a fairly new field. It's the intersection of all the fields you see up here on the screen, and it emerged from the realization that a number of fields shared a common concern with questions of what are intelligent systems, what is information processing, how can we understand it the way you would understand a computer program. And so this is relevant, of course, to understanding people, but it's also relevant when people try to make intelligent machines in computer science. And when they connect the information processing to the brain, it's neuroscience. And how we might look at things in general is informed by philosophy, and the study of language is a special area that has its own field, and psychology does the empirical research on how people actually do things. So cognitive science is probably the best identification, but we're a little bit of all these things that you see here on the screen. I think the one thing that's left out from that graphic, and that's in this one, is the education. Cognitive science is really the theoretical issues, the scientific issues behind education. And so when people study memory, learning, perception, and thinking, the goal is that it should help inform things that happen in the real world.
I think what I would add to that is that I tend to look at things from a developmental cognitive science perspective. So I'm interested in things like developmental patterns across ages and grades, learning trajectories, conceptual change, how it is that students, and I've particularly focused in math and science, how do they get through those difficult passageways in learning where they have to do conceptual change and restructuring?
So, and I think that you two as cognitive scientists seem to be focused on two areas, adaptive learning and perceptual learning. So if we first start with adaptive learning, and I guess either one of you could go, what is it about adaptive learning that attracted your interest?
Well, the motivation is really this whole cognitive science idea and a lot of work in what's also called the learning sciences, to have yet another term. It's really paying off. There are some real advances, real discoveries that have remarkable potential to help with teaching and learning. And that's what has really propelled us. I, in particular, was a basic scientist without a real applied focus, but things that were coming out of our research and other people's research were just too compelling not to see them used out in the world. I think a way to get started with adaptive learning is to focus on some problems that come up in real learning context. So in conventional instruction, for various reasons, it's not a matter of finding fault, but just in terms of practices that we do, And that's both in K-12 learning. It's true in my university when I'm teaching a class of 300 people. But there are some characteristic problems that we have. Instruction does not usually adapt to meet the needs of each learner. Assessment and feedback often come at the end. So we might tell a person at the end, well, you got a C-. Good luck next year. And that's not the best way to use feedback. The fluency of processing is seldom assessed. We often test for accuracy, but not fluency. Learning very seldom guides the learner to mastery based on objective criteria. And learning fails to incorporate a lot of principles we know about learning from scientific research. So these have all propelled an interest in adaptive learning technology. What the teacher does in the classroom is absolutely crucial. What can be done with interactive learning on the computer can provide a great complement to that and can address most of these items on this list. A question I kind of like to ask is, what does a third grade teacher do in front of a class of 30 students, each of whom is missing a different part of the multiplication table? There's really no one message you can give or no one activity that's going to address that. So there's simply some functions that are better addressed in a more personalized manner. The adaptive, well, actually, I'll kind of stop there.
And I think, Christine, what attracted you to adaptive learning?
Really pretty much what Phil is saying, the idea that when you are in classrooms, and like Phil, I started out as doing basic research, and I pretty quickly got interested in environments where the learning really mattered. And I see so many students in classes in schools where there's so much variance in the different students in the same class. And I know teachers are being asked to differentiate their instruction and at the same time meet often quickly paced curricula. So I really think that there's a role for the adaptive, what we've learned about adaptive learning, to help help everybody meet those goals with a little more efficiency and ease.
And just personally, I mean, I think you could see that even more so as classes become more inclusive and as class sizes over the last few years have gotten larger in a lot of schools.
Yeah.
How does adaptive learning work?
Well, there's a lot to say about that. The adaptive learning system that we've developed in the last several years has a number of key elements. First, it's thoroughly interactive, so students are always being asked to do things, and that's a great way to learn. It's better than just presenting information. We're always objectively measuring speed and accuracy in these interactions, which gives us really an amazing stream of continuous assessment data. And at the heart of it are these patented dynamic sequencing algorithms that use the individual's performance to implement a number of laws of learning. They tell us how to vary the spacing and sequencing so that various things that are being learned will proceed to the goal of mastery in the best possible way of folding everything together. We track performance also in this system to objective criteria of mastery, which is a nice thing. That's an idea that's been around for decades, but it's been hard to implement without the kind of computer technology we have now. Underneath all this is a priority score system. So I'm going to tend to talk in terms of learning items for the sake of examples, but I want to point out that this is going to apply just as well to learning procedures or learning classifications or structural categories, higher level concepts. But in any case, there's something that you're trying to get to be mastered, whether it's as simple as a multiplication fact or as complicated as a transformation in algebra. And you're tracking this, and every such item or category has a priority score in the system. And priorities get updated as trials go by based on the learner's performance. So were you fast or slow, accurate or not accurate? What have you had in the meantime? And so forth. And so all the items are actually competing to be what comes up next. And as a result, each individual learner gets a unique path through the learning. A lot of the laws of learning that I'm referring to involve what it's going to take to get something remembered and then retained. So there are dynamics of short and long-term memory. If you missed a problem, there might be an idea that you want to present that again right away, but actually that's not the case. There has to be some spacing in order for long-term memory to engage. I won't go into many of these laws, but you can jointly implement a number of these laws of learning in the same adaptive framework because they're all feeding into item priorities, and then the priority system is determining what gets presented next for that student at that time. A result of this is that learning gets focused where it's needed most, and another piece of this is you can take out well-learned items or categories and keep the learning focused on what still remains to be learned. So overall, learning gets to be much more comprehensive than in almost any other system.
And can you just show that dynamically?
Yes, we have a little demo. This is not in some ways wonderfully elegant, but I think it will show some of the features of this system. This is all an algorithm that has very adjustable parameters for different material and things. But I think we can show the behavior of the system, and that will be the most helpful. As I said, I'm using simple memory items as the example because they're the easiest to illustrate. But this also works with sequencing of different concepts where each example that the student would see would be a new one, but illustrating the same concept. But let's keep it simple. Let's say the student is trying to learn multiplication tables. The software presents something like 4 times 5. Let's say in this case, the student gets it incorrect. What we see in this stack to the left, and I hope you can all see my cursor, is the problem 4 times 5 has gone to a certain place. It's got a pretty high priority because the higher priorities are higher in this stack. But notice that it's not going to be the next problem presented to the students. This is what we call an enforced delay, and the computer simply implements parameters that we have. So having missed an item, we know that the feedback we give to tell the student the answer is helpful, but it's still going to be the case that that item is not well learned. So the learning strength is low. That item should come back soon, but it should not come back until there are 1 or 2 intervening items because you don't want the feedbacks to still be in the short-term memory. So another principle, well, let's just answer this 1 times 7. Let's say we get this one correct and fast. Now you see in this simple illustration, we get the 4 times 5 back. In the actual system, it may be 2 or 3 intervening trials before this comes back, but this just illustrates if you're incorrect, there's a high priority for the item to return soon, but not immediately. And that's the intersection of a couple of laws of learning that we know about. Now, what about that 1 times 7 that we answered? Well, we show it going to the bottom of this stack of 8 items. In reality, if we answered it really quickly, it might be 20 or 30 trials before it comes back, because the underlying theory here, borne out by a lot of scientific research, is that there's a variable of learning strength. And the stronger your learning is, the longer it should be till you're tested on that item again. In other words, you get the best bang for the buck for a well-learned item by having long spacing intervals. Let's do another one. Let's say 4 times 5 has come back, and now let's say we get that correct and fast. 8 times 6 comes up, and we're going to select here correct slow response. So let's say the student gets it, but really has to think about it for quite a while. Now it goes not as far down as a fast response that was correct, and it doesn't come back as quickly as an incorrect response, but it's somewhere in the middle. So there's actually an automated function of response time that the faster you are, the longer it will be until the item returns. And so if you're accurate but slow, it gets a pretty high priority for coming back soon. And of course, it's competing with other items which may be due to come back as well. And what this does is probably gives the best implementation of just a wealth of studies about spacing. Really what you want to do is tune the spacing intervals to the learning strength for that item and that individual learner. And this is the reason this is a patented system is that no one had ever done this or put this into practice or thought of this. And it's just a jump ahead of other systems which tried to do this, and especially in research context, with fixed spacing. Assuming you're going to get better on an item, well, We'll show it to you at small intervals at first, and then we'll stretch those out. But this program really checks for this individual how well something is learned. So I hope that little demonstration gave some of the sense of the individuality of this and how the system is using both accuracy and the fluency of the response, which is measured here by speed, to figure out the priority of items. And then items are all competing to come back. The only thing that's not in this demonstration, even in a crude way, is that items that meet certain objective criteria of speed and accuracy will be taken out of the set, and then learning will focus on the remaining items that still need to be learned. It's also a great system for somebody to come back to for quick refresher training, and there's a mode in which we can see if they know everything, in which case they're finished, or some of the items then go back into a learning mode. So that's something of an overview. Let me see if we have a kind of a summary of that. I think we've, I guess I would only say that research shows that these kinds of techniques cut learning time roughly in half. They give better retention than most techniques, and the separate function of removing material that's mastered is just a wonderful thing for focusing the learner's time where it's needed most.
So today, it seems to me that almost every online learning application says that it's adaptive, or that it offers individualized instruction. So if let's say I were an educator and I were looking at programs which say they were adaptive, what's the best way that I could evaluate whether that program really is going to enhance student achievement?
Well, there are a lot of things you could look for. The most common use of the word adaptive, I think, is that somebody's going to present a pretest to students and try to figure out what their level is or what they know and what they don't know. And on that basis, they're going to assign them some fixed set of lessons. So it's adaptive in the sense that your initial placement is determined, and that's useful. I mean, there's no question that's a useful thing to do. The system I've just described is adaptive in a much more detailed and comprehensive way. It's actually using the progress of learning in what educators call, we call it iterative feedback, that lets the student get results and get new learning to build on where they are. And this is a much more detailed idea of adaptive learning, and it means that every student traces a unique path through the system. So if you're looking at another system, you might ask about it, is the system based on research on laws of learning and memory? Which, if you're just giving a pretest to put the student at the right level, that's a good thing, but it's not then going to implement research on learning and how you're doing the learning after that. So a system should implement those laws to optimize spacing, sequencing, and mastery. Does the system produce a unique learning pathway for each student? Might be a good indicator. Here's an important one. Does the system incorporate both fluency and accuracy? Now, we use the word fluency instead of the word speed because fluency is a very important concept in math learning and many other domains. One might know the answer to something, but if it takes a lot of time, that's the speed part, or if it takes a lot of effort or attention, the person will not be equipped to go on in a hierarchical domain like mathematics to build on that learning. You have to master things in mathematics to the point where you can build the next thing on top of it. Otherwise, it all falls down. And this is something we rarely check for, even in the tests we give in most math classes. So the system we have is assessing fluency by means of speed. Speed will tend to get better as you get more automatic with something, and it goes hand in hand with being accurate. So a system that looks at both fluency and accuracy has a lot of advantages, and those advantages are both in determining the spacing during learning, but also in determining when something has been mastered. If you check just for accuracy, it might be shaky, and it might not last very long, but most of all, it might be hard to build future learning on top of that. But if you get to criteria of accuracy and fluency, you're good to go. And then the last part.
Oh, sorry. Go ahead.
I should have ended, but I've got one last. Does the system track specific components of learning to make sure that each one is mastered? Our system is so fine-grained, and I think what's been missing from a lot of math, learning and assessment even looking at state tests, you look at an item and it's actually involving 3 or 4 components of math knowledge. We really want to break things down enough to get the student where they are and make sure they're getting each and every component of the learning.
So yeah, this is a great checklist. Christine, do you have anything that you'd want to add?
No, I think Phil covered it pretty comprehensively.
Okay, can either of you give some examples of studies that have been done about where students use adaptive learning in math or even in other domains? How did those students fare against students who weren't using adaptive learning?
Well, it's worked out really well. I'm flashing up the title of an article. It's a published article from the Proceedings of the Cognitive Science Society.
And I heard that guy, Everett Medler, is a genius.
Everett Medler is a doctoral student at UCLA and a part of Insight Learning Technology, and he's doing great work. So one thing that we did we've done a lot of studies of these things, but one of the things we've done is compare our adaptive learning system to a classic system developed by Richard Atkinson. Richard Atkinson was both the head of the U.S. National Science Foundation and also the president of the University of California system. So we're very honored to be in his company, but he did his work a long time ago, so by now even he would expect something better has come along, and our results show a greater efficiency of learning, which has to do with how much accuracy you get for how many trials or how much time invested. This graph is a little bit technical, and I'm not going to spend more time on it, but here's a more kind of directly relevant result in the same paper. We tested this adaptive learning framework with students learning multiplication facts in 3rd grade, and these are all students who attended an online school through an online learning company. And in our study, and we call this the ART system, Adaptive Response Time-Based Sequencing, the 3rd graders mastered multiplication through 12 times 12 in an average of 124 minutes. Now that's not one sitting, so it's several sittings, but this is software you can come back to and it picks up right where you left off and so forth. And mastery for these students included demanding criteria of accuracy and fluency, and it also required them answering problems in varying formats, including word frames. So this isn't just memorization of the math facts, although you need that, but it's a gateway to the meanings of these things and to word problems. So we don't know of any other result to get mastery of multiplication in 124 minutes. Certainly, we have found in some of our research there are 8th and 9th graders in big city schools and other places who haven't mastered these things. And this is just a gap that haunts students as they try to progress. And it's the kind of thing that we can just address very systematically with this kind of approach.
So it sounds like students really do learn an awful lot faster when the content is tailored to where they're having problems and what they've mastered, according to laws that people have studied over the last 20 years in cognitive science. So let's move a little bit to perceptual learning, which is the other area. And before we start talking about perceptual learning, I want to get an idea of what people's impressions about perceptual learning. So I'd like to throw out a second poll, and so the question is which of these do you think perceptual learning is primarily involved with? Okay, and I think I'm going to close that and share the results. And this is a little bit of a trick question. Christine, why was this a trick question?
Well, this is one of these cases where 3 of the answers are actually perfectly reasonable and only 1 is not. I think it's interesting, though, that the one that didn't get any response is your expertise in a particular domain is actually very relevant to perceptual learning. The one that's not is the visual learners. That's not primarily what it's about.
But in defense of our whole group, being able to see the underlying structure of a situation is, in fact, arguably the best answer here.
Yes.
Uh-huh. And so, Christine, when you said expertise in a particular domain, can you just describe that a little bit?
And so a lot of the research that that the work in perceptual learning is based on has actually been done in expert domains. Some of the very earliest work was in chess. Phil, do you want to maybe flip to the chess example?
Let me go back to Phil.
Yeah. The concept of perceptual learning was first introduced and named by Eleanor Gibson back in the late 60s. And it turns out that a component, when people are really good at something, a component of their performance almost always has to do with their capacity to pick up structure and relationships in the inputs in whatever their domain of expertise is. Actually, Phil, I don't know, maybe you want to pick it up with this.
Yes, you are going to hear, Chris and I have a rough division of labor. She's going to say more very shortly, so that will probably be an improvement. But, but I think we can start again with problems that people experience in teaching and learning, and just as our audience answered, the grasping of underlying structure, or what structure means that you can use a certain procedure or it's a certain kind of problem so you can know what to do. We find that students often fail to recognize key structures or patterns in math and other domains. Students who are taught procedures or facts fail to understand how they apply to new problems or situations, or they apply them in inappropriate situations. And learners may understand but process slowly with high effort or cognitive load. So these are all problems that are relevant to perceptual learning and that we found can be addressed with perceptual learning technology. But your question was really more about what is perceptual learning, and I think we're off to a good footing given the poll results, but I'll give a little contrast here. In the bottom part of this slide, most instruction has emphasized what cognitive scientists call declarative knowledge, and that consists of facts and concepts that you can verbalize. The other thing, which is very important in mathematics as well, is to teach procedures. How do you do long division, for example? But these things are important, but they don't encompass all the learning problem. There's a very important kind of learning that has to do with pattern recognition and structural intuition. And you can even take this analysis further. Two investigators, Bereiter and Scartamalia, have a great metaphor for this. They say that most of us, and by most of us they mean not only students, but teachers and researchers in learning, academics, scientists, everybody, we're in the grip of a mind as container metaphor. So learning is putting things in the mind, and these are objects like facts, concepts, and procedures. We put them in the mind, and then I guess we pull them out on the test. And here's Gary Larson's interpretation of the mind as container. Mr. Smith, may I be excused? My brain is full. So that's a pretty common way of looking at a lot of learning. And what's been realized in recent decades is if you look not at the learning literature, but the literature on experts, as Chris mentioned, you find that the way in which experts differ most conspicuously from novices is not the facts and procedures that they know, but their ability to see what's going on, their ability to classify, what am I looking at? And as Chris mentioned, a lot of the most exciting studies have been done in chess, and I'd love to talk more about that, but I think we should move on because I'll get stuck on chess. I'm even going to pass that. But this isn't just the province of grandmaster chess players who can compete with a machine that looks at 200 million moves a second, but it's something that happens in all of our lives. And what we're going to tell you in a little while is that the perceptual learning part happens very haphazardly in ordinary educational settings, but can be addressed more directly and accelerated. But I'm going to hand things over to Chris here, and she'll tell us about maybe perceptual learning in ordinary life.
Christine?
Yeah?
So,
Can you see my screen now?
oh, do you want me to I can switch
Can you
it
see it?
to?
I think I just did.
Yes. Okay.
Okay. This actually is an example that was comes from medical education. It was done here in my hometown of Philadelphia. They were looking at training, at internists in training who need to be able to identify heart murmurs when they're examining patients. And there are a variety of these different murmurs, and they sound different in different people. And it's a difficult kind of thing to teach if you think about our standard ways of teaching. So if you give lectures or you have students attend classes or read about it in a textbook, or just take years to see enough patients to get good at it, it's a very slow and difficult kind of learning to accomplish. But these researchers at Temple University discovered that by having students listen to many examples of each of the most common types of heart murmurs, they just used iPods to do this, they very quickly got to be almost as good as practicing cardiologists. And this is that kind of learning to pick out what matters in the thing that you're listening to. But it's not just, medical students or people who are experts in radiology or chess or aviation or many of these areas where perceptual learning has been studied. It's also the case that children are good at this. In fact, humans are good at this. This is just a basic human capacity to do this kind of learning. And if you think about little children when they're going around in the world and their eyes are wide open and they're starting to learn words and develop concepts to go with those words, they see things like dogs, and they fairly quickly get to be pretty good at identifying the dogs from the non-dogs, and it can be a little tricky. So there are things that are not dogs, like a fox or a bear or a wolf, that might look like a dog, but they're not. And then if you think about the category of dogs, there's an enormous variety. And the things that we tell kids, like, oh, it says woof woof, and it wags its tail, and it eats dog food, and it's brown or black, those things hardly help at all. And yet kids turn out to be really good at picking out the dog. So you could have a three-legged dog that has no tail and is dyed blue, and the child has no trouble saying, yep, that's still a dog. But it's very hard to articulate what it is that lets them know it's a dog or how they did it, but they're very good at it. So this is a capacity that we'd like to be able to bring into teaching and learning, so that you have that same sense of being able to have that immediate recognition of, I know this thing that I'm looking at. I know what it is. I've seen this kind of a thing before.
So as a teacher, is perceptual learning something that I can implement with my students? Hello?
Hello. Chris? I wonder if we lost Chris.
I think we did lose Chris.
Well, can you hear me?
Okay, I think we can hear you.
Okay, maybe I'll
so
just...
Go
ahead.
So while Chris is getting back on the computer, let me ask you that question then. If, as an educator, is there a way, if as a teacher, could I implement perceptual learning with my students?
Yes, and that's been the real revelation here. I think we're watching Chris log back in, but I'm going to change briefly back to keep it going, and then we'll give it back there. Sorry for the inconvenience here. Okay, so what's really the news in this area is that there are ways to teach this. So people have known for a long time that the seeing part of learning takes a while. They talk about it as seasoning or experience, and it has been often thought of as something you can't teach. But what we've really had a lot of success with is taking elements of what's been done in research on these in laboratories where perceptual learning can often be demonstrated in a short time, and putting them into what we call perceptual learning modules. And the other thing is we've realized these apply to very high-level tasks like mathematics. So some tasks, like reading the letters at your optometrist's office, are obviously perceptual. But when you get to mathematics, you might say, well, what's that about? And the truth is, even high-level symbolic domains have structure and have a seeing problem in them. So people get good at mathematics, learn to see collections of symbols as structured, as different parts of them having certain functions, and transformations of those, as in algebra and so forth, and all through higher mathematics. In fact, it's a tip-off that in math and science and some other disciplines, economics, whenever we start to talk about a complicated problem, one of the first things we do is we make a visible representation, a graph or an equation or a model. And this is to engage routines that have evolved over millions of years to help us use our perceptual system to pick up structure in the world. But mathematical representations are complicated, and the learning problem, the perceptual learning problem, is in any given domain to become able to select what's relevant, to ignore what's not relevant, to discover underlying patterns that make one situation different from another. And then all the factual knowledge you have, all the procedures, plugs right in because you know what you're doing. It also means that perceptual learning is remarkably powerful because if you come to see the right relationships, it doesn't just equip you to do one kind of problem. It may equip you to do lots of problems, which is why in our research we see lots of transfer. If you've gone through a perceptual learning module, we can present to you a math problem that we didn't train you on at all, and the student is suddenly much better than before they started. So these perceptual learning modules have a lot of elements to them, but they involve short classification trials and lots of variation. And we didn't invent perceptual learning. So it's actually the student's brain that's doing the work. If you're presented with the right kinds of inputs, the brain will find the structures that matter. So if you tried to say to the student what all the structures were, you'd experience dismal result. But if you actually have them transact or interact with these materials in a guided way that draws their attention to structural differences and requires them to pick up information to make the right responses, and then you add feedback to again help direct their attention, you get amazing results.
And I don't want to throw things off by too much, but we'd had a conversation a couple months ago involving subtraction where you made clear that if a student heard these two different problems, one, John had 4 pieces of candy, and he gave 2 to, well, that's too easy. John had 7 pieces of candy. He gave 2 to Sally. How many pieces does he have left? Versus John has 7 pieces of candy. He has 2 more than Sally. How many does Sally have? And that students will think that those are 2 very different types of problems, where in fact, people who are good in math know in either problem you subtract 2. Can you relate that the way you did for me earlier to perceptual learning?
Yes, and I'll hand back to Chris. I think she's back online.
Yes, I am. Sorry, everybody, that I got bumped off there for a minute. Yeah, so the examples you just gave, Mitch, have an underlying problem structure. The first one was a case where you have a set that's being separated into 2 sets. And the other one is where you have 2 sets that you're comparing, and you want to see what's the difference between those sets. But a lot of students have a tendency to just grab numbers. If they hear a problem like that, they'll grab the numbers and they'll throw in their favorite operation because they just really aren't quite sure how to take that problem as it's expressed in words and find what the underlying structure is and then translate that into the representation of the number sentence. And that's the kind of thing that perceptual learning is really tremendously helpful at, because when students practice this problem of finding the structure in the word problems, they come to realize that there are really only about a dozen or so problem frames that capture those kinds of word problems that involve 3 whole number quantities. And they can get to be very good at looking at it and seeing, okay, I see what this problem is about, I see the structure, and then they're ready to translate that into a number sentence and then, solve it to get an answer.
Yeah, it's a bit of a revelation to all of us that word problems have structure. And maybe it's fairly easy to realize that equations have them or graphs have them. But in order to read a word problem when somebody does it correctly and does the right mathematical operation, they're using the symbols in language and their structure and relations to provide a direct route to a mathematical instantiation of that. And that's a skill that we haven't had a good way to practice that. We've known that some students get it and a lot of students don't get it, and it's kind of been hard to address.
And that talking often doesn't do that. These kinds of things do get discussed in math classes, but for a lot of students, the talking it through doesn't get them there.
And so where perceptual learning has been applied purposefully to students, are there studies that show that students learn better or faster?
Yeah, there sure are. I can give you an example of one that we've done. This is actually a research study that is the research prototype for something that we're now starting to distribute to schools. This is what we call multi-rep, and it's a similar kind of issue to the one we were just talking about, where students see all of these different mathematical representations, and they're not very good at seeing how do you find the real meaning in it. And if you think about things like equations, graphs, and word problems, you can have the three different formats that look very different from each other, but they can all be expressing exactly the same mathematical idea behind them. And with the multi-rep in the research study, we had the students practice this. So they would see something like this at the top of their screen. They'd see a target in one of the representations, in this case a graph, and they have to choose which of the three at the bottom matches to this. And over time, they get to be better and better and better at knowing where to look to find the relevant information in each format. So they come to realize, where is slope in the graph? Where's an intercept in the equation? How do I connect this part of this to what I'm looking at in an equation? And with practice, they get quite good at this. This is another example of going from a word problem to a graph. And students start to pick up clues like, oh, let's see, is this going to be a positive or negative slope? I can get to that pretty quickly. Is there an intercept here or not? So they come to look at it with the expert eye and become much faster at being able to do these kinds of things. The software gives them feedback every step of the way, which speeds up this process of learning for them, helps them start to see how to map one thing to another. And then when we do the research studies, we actually do pre-tests and post-tests, and most importantly, we give them transfer tasks to see, can they take this skill that they've acquired in the computer environment and apply it when the computer's not there anymore and they're doing something else and they're looking at the kinds of problems that they might be seeing in a class or on a test of some kind. So this is showing the improvements that we see from pre-test to post-test. The pink bars are the post-test. The students get much better. They're much more accurate. This is percent correct here, at being able to take a representation in one form and create it in another. So they don't have to create it in the software. They just have to practice mapping it, but they actually get better at generating it. We also see an improvement in solving word problems that are open-ended. So again, they're starting to move that outside of what they've been practicing in the software. And they're able to accomplish this with just a couple of 2 to 3 classroom periods in which they're practicing this. We get the transfer, and in this case, we also compared them to a control group that actually practiced exactly the things that were on the post-test, but they did not get they didn't show as much improvement as the group that was using the perceptual learning software. So there you have an example of how it can help.
Okay, thanks. And earlier we were talking about adaptive learning. Can adaptive learning and perceptual learning be combined?
Yes, I think we'll switch back here for a second. And so they can be combined.
Practice, you get a quick review.
Yes, if maybe your unconscious brain can process at that speed, and mine can. So most of our software incorporates both perceptual and adaptive learning. And as I mentioned, when you're using adaptive sequencing and spacing with category learning, as Chris was describing in multi-rep, each problem you get is a brand new one. So you saw dollars and products and grams and moles, and the particular numbers and slopes and things and problems were all different. So it's the extraction of structure that's going to transfer to new cases, and different types of problems can get tracked and sequenced and spaced by adaptive learning. So here's another, I think if my screen is now visible, in another perceptual learning module that we have researched heavily, which is about algebraic transformations, we try to address the seeing problem in algebra. And the students who were real school students in 8th and 9th grade taking Algebra 1, we got to them at mid-year in Algebra 1. And so the school was doing a darn good job, because at mid-year in Algebra 1, if presented with basic equations like x minus 4 equals 8, the students were average, on the class average, 80% correct. This tells us they understand the declarative and procedural components. They know you're supposed to do the same thing to both sides. They know what solving for x is, and they can do it to some degree. The real revelation for us, and which we kind of suspected, which is why we're heading into this, is there's a seeing problem in algebra. Remarkably, students look at something like x minus 4 equals 8, and they average 28 seconds per problem, whereas somebody who's been doing this for a while looks at this and kind of just sees the answer. They're seeing, the way we see objects and events as undergoing transformations in the world, you kind of see those transformations in algebra. This is not an innate skill. This is something that's not, that either is addressed haphazardly for some students or not at all for others. So we designed a module which has become the basis of our Algebraic Transformations product, Algebra Insight Transformations product, where we don't have students solve equations. We give them strings, sometimes quite complicated strings. We give them an equation, and then we give them choices of several possible transformations, only one of which is a legal transformation. So if you look at this for a while, and this is a pretty complicated one, believe me, we start a lot easier than this, but you can see that this term, in parentheses, 4 plus y, has moved from one side and has been divided by both sides. So this is probably the answer, yes. So there's a highlighting that says it is. And students do those and get feedback. But here's a case where we're using the adaptive learning to track different kinds of transformations. Maybe the student is not seeing appropriately what happens when you divide both sides. That's actually, in some internal analyses we've done of research data, dividing both sides turns out to be a lot easier than we thought. It's subtracting from both sides that's hard. And of course, anything that has to do with negative numbers, multiplying both sides by -1 or something is a misery for kids. So we're tracking these separately. And if the student is really competent in one kind of transformation, they'll see fewer of those, and they'll see more problems that call upon the skills that they're still developing. And in the end, they'll get tracked to mastery on all these. Let me tell you quickly some data from this. 2 to 3 40-minute learning sessions. So we got into a math classroom for a couple of days, and a pre-test and a post-test flanking those. Learners did not solve any equations in the learning phase, but in this graph on the left, direct your attention to solve problems. These are actual equation solving tests that were given before and after using the perceptual learning module. At the beginning, here's that 28 seconds I was talking about. Solving simple equations took a long time. After 2 or 3 days of this, just recognizing and mapping these transformations, students came down to an average of about 13 seconds a problem. And a week or 2 later, in a delayed post-test, they were even a little lower, about 11 or 12 seconds a problem. So 2 or 3 days of 40 minutes with this module brought about a relatively permanent change, and a permanent change in their fluency, because they could already, to a pretty good standard, do this task. But the seeing, we have energized the seeing problem of algebra, which presumably makes all kinds of things go better in the math that's building on this.
So, and actually, I want to throw this something to the people who are watching, is that if you have questions that you'd like us to address, because we're getting close to an hour now. So if you have specific questions, if you can open up that where that red arrow is on the screen, and there's a question and chat area, and ask those questions, we can address those. I'll tell you a question that I wanted is, right now in education, everybody is focused on the Common Core standards. So, I'd like to kind of shift a little bit. Are there areas that adaptive and perceptual learning are especially suited that apply to the Common Core standards, and especially Common Core standards in math?
Yeah, very much so. I think if you look across the Common Core standards target several kinds of learning, and it runs across grade levels from the elementary right on up through high school, where both of these can play really key roles. So one is anywhere students need to have this kind of fluent mastery. So for example, starting in the elementary grades, there are explicit Common Core standards that say that students are supposed to be fluent with addition and subtraction facts through 20 by the end of second grade, and with multiplication and division facts and with factors through 100 by about the end of fourth grade. And a lot of research actually supports this goal in the Common Core, that real fluency, being able to work with these math fact families and with the operations quickly and effortlessly using mental math, that provides an important foundation for making smooth progress then in subsequent math learning and in problem solving. And adaptive learning is really ideal for helping students achieve this much more efficiently. And then I think a second area is where the representations and notations that are used in math need to become more intuitively meaningful to students. I think for so many students, math sort of just continues to look like a foreign language to them year after year after year when they encounter decimal notation, fraction notation, algebraic equations like the ones we were just looking at, various sorts of graphical representations. Students don't know how to see through these representations to the meaning so that it's transparent for them. So they struggle with a lot of inefficient and error-prone kinds of procedures. And this is a case where the perceptual learning we've been talking about is a really powerful complement to the other kinds of learning activities that students are participating in. It's one that really engages this kind of intuitive expert extraction of structure.
And I guess we're rapidly approaching 3 o'clock. We may go a little bit over if people have time. I do want to explain to people that there's a questionnaire at the end when you log out, and we really would appreciate it if you could fill out that questionnaire, because that'll determine if we do future webinars on this topic or other topics, and will help us improve webinars as we go. One thing that is interesting to me is that we hear so much about games, and kids need more games, and then they're going to learn everything better. What does cognitive science say about games? Are they effective for learning? And what can we learn from games that we can apply to education?
Well, there's certainly elements, they're game-like elements that are important in implementing good learning and cognitive science principles. But on the whole, there's been pretty bad results with what I would call the spoonful of sugar idea, that you can give the student a story or a game and embed some mathematics in it, and they're going to, the medicine will go down with the story or the game, kind of incidental learning of the math, for lots of reasons, one of them having to do with something called extraneous cognitive load. They learn the game or the story and not the math. There's been a recent review of this that's gotten some attention. It's called Our Princess is in Another Castle. It's by Michael Brown and some others. And so people can look that up on the web. But it's actually shown that in math and science areas, there's no evidence for games improving learning up to this point. There's a little bit of evidence in history and some in physical education where there are exercise games. But that's, I think there's two parts to answering your question, Mitch, and one of them is we should be on the alert for anything that motivates our students, but we're not likely to get them to accidentally learn math while being motivated to do something else. What we have to do, if we help them to see the structures in math, to make them meaningful, to show them that mastery is possible, to engage them where they are and give them progress, there's a lot of satisfaction and a lot of engagement that can come from that. But of course, we're always looking to add to that. We find different kinds of feedback help. We find that students realize that they're learning as they get faster and more accurate and take on new things. And that's kind of the intrinsic motivation, which, by the way, will also lead them to use math when there's no longer the external reward of a game. So there's elements that we look for in gaming on the motivational side and also on the cognitive side. Feedback, reinforcement have both a motivation side and a cognitive side. But the general idea that just make a game out of it and something good will happen is contradicted by a lot of research, and in fact things are often quite a bit worse than a plain vanilla presentation when they are in a game. So there's not magic in simply having a game. Our approach to this is to get deep math content and make it adaptive so students engage where they are, and then give them the seeing of structure that their brains are going to do the real work in getting that. But those satisfactions and the stepped progress are, I think, a good path for making technology useful, whereas simple magic of saying it's a game is not. It has not proven to be.
And is there any evidence for or against that that having a storyline behind a game adds to the cognitive load and inhibits learning, or is that just something that people are making up?
No, that's from head-to-head comparisons where they do the story plus the math versus the plain math, and the plain math wins, gets better learning results. And the interpretation, I think there's always theory and data. So the interpretation of that is it seems to be extraneous cognitive load. And that interpretation fits with a lot of other more basic research studies where people have studied cognitive load. And that's, intrinsic cognitive load. If a task is difficult, because intrinsically it has these parts to it, then that's something learners need to cope with or have to be helped to cope with. But there are a lot of studies that vary cognitive load for things that don't have to do with the real learning that needs to take place. So we know from the basic studies there is an effect of extraneous cognitive load. Having a story plus math seems to fit that description, and in a lot of head-to-head comparisons that just makes things worse.
Okay. Well, I have to say I've learned a lot. And I hope that we can do some more webinars and that other people learned a lot also. Just if a school were interested in the modules that you have so far, the two around algebraic transformations and multi-representations, or the one so far for elementary students, the operations in algebraic thinking, how would they get hold of you?
Well, I'm not going to avoid that question, but I will say first I put up a little math joke since we have a sophisticated audience. This is actually a perceptual learning math joke, although we didn't make it up. But it's the applying a procedure to the wrong structures. And teachers out there may well recognize when their students have divided a numerator and a denominator of two different fractions that were separated by an equal sign, which is not the right thing to do. But here are some current products from Insight. On the perceptual learning side, in algebra, the Algebraic Transformations product, which has a couple of levels, and our multi-rep product. And then in elementary, the core math uses adaptive learning, as in that study where third graders learn multiplication so well. Any of the operations are present, all kinds of combinations, which is a good thing to do as students progress. And then different levels of word problems, including the typology of word problems that Chris was mentioning, to get into the more sophisticated issues with word problems that really do trouble so many students. so this module covers several grades and goes all the way up into factors and gets people into some of the pre-algebra content that's so crucial, and sometimes it's just a bit of a black hole in some students' learning.
Okay, and again, the website is math.insightlt.com. And if you're interested in finding out more, please email any of us, or mostly Chris and Phil, at info@insightlt.com. And thank you, everybody, for attending. And again, please fill out the survey at the end as you log out, and let us know what you think and what we can do to make webinars better and topics that you might be interested in. Thank you, everybody.
Thanks, everyone.